Hello, welcome. I'm going to go ahead and try to make this video pretty quick. We are going to pick back up with some of the implicit differentiation techniques that we left off with last Wednesday. And I want to get through just a few more examples, just something that'll get us to a good point so that when we do pick back up with the notes this Wednesday, we won't be too far behind. So let's go ahead and let's dive into example 118, where we're asked to find the equation of the line tangent of the circle x squared plus y squared equals 1, which passes through the point 1/2 negative root 3 over 2. So the idea here is that what we're given is we're given this implicit equation. We're given the equation that reads x squared plus y squared equals 1. Now, what we could do is we could go use some algebra and we could try to solve for y and figure out which y values will give us an x value of 1/2 and a y value of negative root 3 over 2. Or we could use this technique that we talked a little bit about last week called implicit differentiation. And the idea behind implicit differentiation is that we're going to take the derivative of both sides of this equation with respect to x. And now as I'm looking at this is saying perform the operation of the derivative with respect to x to x squared plus y squared, and then on the right side, take the derivative of 1 with respect to x. So if we start off on the left side, what this is really saying is we can treat this differential operator, we can essentially distribute it over x squared and y squared. So we could think about this as take the derivative of x squared, then take the derivative of y squared, and add the results together. And then on the right side, this is going to say take the derivative of 1, but we know that the derivative of 1 with respect to whatever variable we're going to differentiate with respect to is just going to be 0. Okay, so now we can kind of slowly step our way through this. So what I've highlighted in yellow over here all the way to the left says just take the derivative of x squared with respect to x. We know that this is just going to be 2x. So at this point, we have done nothing new. Now, what we want to do is we want to take the derivative of y squared with respect to x. This is a new idea, but I think we can follow through with it, right? So what this is saying is it's saying I have some function. Maybe I'll just pretend I have a function u. And what's happening to that function u is it's being squared. And we want to take the derivative of this function u squared with respect to x. Well, this right here, we know is just exactly precisely the chain rule. So we know that when we take this derivative, this is going to be 2 times u prime, or du dx. Well, there's nothing special about taking the derivative of u squared. This could be the derivative of w squared with respect to x, the derivative of z squared with respect to x, or the derivative of something like y squared with respect to x. So if we rearrange all of our letters, or if we change all of our u's to y's, what we have is the derivative of y squared with respect to x is going to be 2 times y times the derivative of y with respect to x, dy dx. I'm going to go ahead and I'm going to delete this. So what we have now is now we finally have ourselves a derivative. We have something that we can start using to find slope. It's not solved for at this point, but we can do a little bit of algebra to get us there. So what my goal is now is going to be to try to isolate this dy dx. And I think we can see the little bit of algebra that we're going to have to do to get there. If we subtract 2x from both sides of the equation, we'll have a 2y dy dx equals negative 2x. And then if we divide both sides by 2y, we'll be left with dy dx equals negative 2x over 2y. The 2's can cancel, and we could just call this negative x over y. So what we have now is we have ourselves a derivative. And remember, derivatives are synonymous with slope. So if we want to find the slope of the tangent line, what we want to do is we want to evaluate the derivative at the point 1/2 negative root 3 over 2. This is a little different than most of the derivatives that we've taken so far, because in this case, we're not only just plugging in an x value, we're also plugging in a y value. But we can go ahead and we can see that what I want to do is I want to replace x with 1/2, and I want to replace y with this negative root 3 over 2. So this will leave us with a negative 1/2 divided by a negative root 3 over 2, which will simplify to a 1 over root 3, or we could call this root 3 divided by 3, getting ourselves a rational denominator. Right? So what we have here is we have our original function, the circle x squared plus y squared equals 1. We've taken the derivative using implicit differentiation, and now we have ourselves a slope. Well, if we're looking for the equation of a tangent line, keep in mind the two things that we need in order to find the equation line are a point, which we were given, and a slope. So now we just need to tie those two pieces of information and write down the equation of the line tangent to the circle at the point 1/2 negative root 3 over 2. And that'll be y equals our slope, which is root 3 divided by 3, times x minus the x coordinate of our point, which is 1/2, plus the y coordinate of our point, which is negative root 3 over 2. Now, we could take this a few steps further and take it down into slope-intercept form, but because that was not asked for in the instructions, I'm going to go ahead and I'm going to leave the answer here. So just to recap, the thought process is identical to the thought process from earlier in the semester. If we're asked to find the equation of a tangent line, we want to take a derivative to find slope. If we're given a point, awesome, we can go ahead and we can use that point and combine it with a slope to write down the equation of a line. Let's go ahead and let's move on to the next example then. So example 119 says given this relation or this implicit equation, x squared times y plus y squared equals x plus 1, here we're asked to find dy dx, and then we're asked to determine the behavior of y at the point 0, 1, and then determine if y is concave upwards or concave downwards at the point 0, 1. This is a pretty tricky question. This is definitely a tricky question, but I think we can go ahead and we can work our way through it. So first of all, let's just start by finding dy dx. So what this means is we want to start off with our original equation, which in this case was this x squared times y plus y squared equals x plus 1. Now, because we want to find dy dx, what we want to do is we want to perform the derivative operator to both sides of this equation. I'll use slightly poor notation here, but I'm saying I want to take the derivative of this whole equation. So now, what's going to happen is the first thing I see is we're taking the derivative of this x squared times y. That does require the use of a product rule, but that's okay. We know the product rule. We know how this is going to go. So the first thing we're going to do is we're going to take the derivative of x squared with respect to x, which will just be 2x, and we'll leave y alone. Then we're going to leave x squared alone and take the derivative of y with respect to x. We don't know what y is, but we can still take its derivative with respect to x. So we're just going to write either y prime or I prefer dy dx. So now we've taken the derivative of x squared times y. We'll move on to the derivative of y squared. This is something we should be familiar with. We've already taken this derivative in the last example. This is just going to be a 2y times dy dx. And then on the right side, we're taking the derivative of x plus 1 just as we normally have. We're still differentiating with respect to x. I know the derivative of x with respect to x is 1, and the derivative of 1 with respect to x is 0. So now at this point, now all we have to do is we have to solve for dy dx. So what I'm going to do is I'm going to actually begin by factoring out a dy dx from those two terms, And I'm going to move that 2xy from the left side to the right side by subtracting. So if I factor out a dy dx, that leaves me with dy dx times x squared plus 2y. And that's going to be equal to 1 minus 2xy. Finally, we can go ahead and we can solve for dy dx just by dividing by that x squared plus 2y. And now we've actually got ourselves a nice derivative. This is a derivative. This tells us the slope. This tells us how y changes as x changes. The difference now is it is now a function of two variables, meaning that it depends on both x and y. However, other than that, it's identical to the derivatives that we've been taking all semester long. So I think we can check off our first box now. We have found dy dx. The next part of the question asks us to determine if y was increasing or decreasing at the point 0, 1. So to figure that out, what we're going to do is we're going to evaluate our derivative at the point 0, 1. So all I'm going to do is I'm going to replace all the instances of x in my derivative with a 0, and I'm going to replace all the instances of y with a 1. So what that's going to give me is 1 minus 2 times 0 times 1 is just going to be minus 0. Then in my denominator, we're going to have 0 plus 2 times 1 is just going to be 2. So what we're left with is 1/2. So now we have to think back to our section on curve sketching. If the derivative is positive, which 1/2 is, this tells me that y is going to be increasing at the point 0, 1. So we've got ourselves a derivative, and we've also determined that the function is increasing at that point 0, 1. The last part of this question asks us about the concavity of y. So basically, how is this curve behaving? Is it concave upwards or is it concave downwards at this point? And remember, concavity comes from the second derivative. So here we're going to want to go ahead and take the second derivative of our function. And I'm going to claim that the easiest place to start is going to be right here. So we're going to go ahead and we're going to start with our first derivative. We're going to differentiate our first derivative again with respect to x. And that's going to give us our second derivative. So let's go through and start thinking through our second derivative. So in order to take our second derivative, we're probably going to want to go through the quotient rule. So let's start thinking through our quotient rule. Quotient rule says low times d high. So our numerator is this 1 minus 2xy, or 2x times y, which does require a second use of the product rule. So derivative of 1 is 0. We'll take the derivative of 2x. That's going to leave me with 2. Leave y alone. And then I'm going to leave this negative 2x alone and take the derivative of y, which we can write as y prime or dy dx. I'm going to give myself a little bit more space here. So at this point, we have our low times d high. Minus, now we're subtracting off our high function, which is 1 minus 2xy, times the derivative of the denominator. Well, the denominator was this x squared plus 2y, so its derivative with respect to x will be 2x plus 2 dy dx. And that's all going to be over the original denominator squared. Now, last but not least, we just need to evaluate our second derivative at the point 0, 1. Okay, so what's going to happen is now I'm going to go through, and everywhere there's an x, I'm going to replace my x with 0. Everywhere there's a y, I'm going to replace that with 1. There are also some other instances that we will have to address a little separately. So let's start going through. So first of all, this x squared plus 2y, that's just going to become a 0 plus 2 times 1, which is just 2. Then inside the brackets, we'll have negative 2 times y, or negative 2 times 1 is negative 2, minus 2 times 0 times dy dx is just 0. Now we're subtracting off 1 minus 2xy. Well, x is 0, so x times y is also 0. Times 2 times 0, 2 times x becomes 2 times 0, plus 2 times dy dx. Well, remember, dy dx at the point 0, 1, we already evaluated dy dx at the point 0, 1. That gave us a 1/2. So when I evaluate dy dx at the point 0, 1, that's just going to leave me with a 1/2. And this is all going to be divided by 0 squared is 0, plus 2 times 1 is 2, squared is going to be 4. So if we do go ahead and we evaluate this, we're left with 2 times negative 2 is going to be negative 4, minus 1 times 1. That leaves us with negative 5 over 4, which is less than 0. Which means that if we were looking at our graph at the point 0, 1, we can claim that it is in fact concave down. Okay. So let's go ahead and let's take a look at example 120 then. So example 120 asks us to find the equation of the line tangent of the curve given by sine of xy equals sine of x plus sine of y passing through the point 0, 0. Okay, similar idea to example 118. We're given some sort of implicit relationship between two variables, and we're asked to find the equation of a tangent line. So I'll approach this one slightly differently than the last one that we approached. This one, I'll go back to basics and say that there's two things that we need in order to find the equation of a line. We still need a point and we still need a slope. Our point was given to us in this case is just the point 0, 0. Our slope is a little bit harder to find because we're not given a function of x in terms of y or a function of y in terms of x where we can just easily take a derivative. What we have to do here is we have to start off with our implicit relationship, sine of xy equals sine of x plus sine of y. We still want to find dy dx. And in order to do that, we are going to want to take the derivative of both sides of this equation with respect to x. However, we're going to have to take implicit derivatives because we have an implicitly defined function. So we'll go ahead and we'll start on the left side. We know that the derivative of sine is cosine. And we know that whenever we're taking the derivative of sine of u, it's going to be cosine of u now times the derivative of what's on the inside. So now we need to multiply by the derivative of x times y, which does require a use of the product rule. So if we take the derivative of x with respect to x, that leaves us with 1. We'll leave y alone. Plus x times the derivative of y, we're going to write dy dx. Now on the right side, we have the derivative of sine with respect to x. The derivative of sine of x with respect to x is just going to be cosine of x. And the derivative of sine of y with respect to x is going to be cosine of y. But the chain rule applies here because we're not taking the derivative of a function of x with respect to x. We're taking the derivative of a function of y with respect to x. So here we have to multiply by the derivative of y with respect to x, which is dy dx. At this point, there's actually a couple of different places that we could go from here. So in example 118, we actually went through the entire process of finding dy dx first before actually substituting in our x-coordinate and our y-coordinate to find dy dx. That's not actually entirely necessary, because if we would want to, we could actually make a claim that if we were to plug in if we were to plug in our point now, we could actually solve for dy dx. So let's say at the point 0, 0, what I'm going to do now is I'm going to plug in 0 for x, 0 for y, and let's see what happens. So we'll be left with the cosine of 0, which is 1, times y plus x dy dx. Well, y is 0, x is 0. That's going to be equal to cosine of x, which is 1, plus cosine of y, which is also 1, times dy dx. So what we have is we have an equation that looks like 1. So what we have is we have an equation that looks like 0 equals 1 plus dy dx. Solve for dy dx, and we're left with dy dx equals -1. So what we have is we have our point, and we have our slope. So with that information, we can go ahead and we can write down the equation of the tangent line. So it's going to be y equals -x minus 0 plus 0. At this point, if we wanted to leave it here, that's fine. However, it's not ideal. Let's just take it the one simple extra step and rewrite this in slope-intercept form. So if you can imagine distributing that negative sign, you'll be left with y equals -x plus 0 plus 0. The plus zeros don't impact the answer at all, so we can leave this as y equals -x. Okay. Now, there are a few more examples that I want us to get through, and I think we can get through each of these relatively quickly. So what comes up next is what we call the derivatives using the natural logarithm function. If you remember back to early on in the semester, we had talked about the derivative of e to the x, and we've talked about the derivative of the natural log of x. However, there are other quantities that we can raise to the x power. We can take y equals 2 to the x, or y equals 12 to the x, or y equals 10 to the x. The only variable to be raised to the x power, or the only number raised to the x power, does not necessarily have to be e. And we'd like to be able to take the derivatives of these other functions, of these other expressions. So that's what we're going to begin playing around with in example 121, part A. So let's start off by taking a look at what we have. We have this expression that reads y equals a to the x. The space here is intentional. I don't know how to take the derivative of a to the x. Unless a is equal to e, I have no idea how to progress forward or proceed forward with taking this derivative. So what I'm going to do is I'm going to mentally search for a list of functions that allows me to work around exponents. Maybe a function that allows me to pull exponents out of the exponent. And that function is one of our log functions. And really, the log function that we know how to do calculus with is the natural log function. So what I'm going to do is I'm going to take the natural log of both sides of my equation. And what the natural log function allows me to do is it allows me to bring the x and the exponent out front of the natural log. So this is a property of logarithms that you learn about in something like a pre-calculus class. Now what we can do is now we can actually apply this technique that we've been discussing. We can actually implicitly differentiate both sides of this equation. As far as the left side is concerned, the derivative of the natural log of y is going to be 1 over y times the derivative of y. And on the right side, we're taking the derivative of x times the natural log of a. Well, if a is a constant, the natural log of a is also a constant. So what we're doing here is we're taking the derivative of a constant times x, which is just going to leave us with the constant. So finally, we could actually write down the derivative of y with respect to x is going to be y times the natural log of x. However, it's often not preferable to start off with a function of x, y equals a to the x, and say its derivative is now in terms of the dependent variable. So what we do is we just recognize that y itself is equal to a to the x. So we're going to come over here, and I'm going to replace y with a to the x. Forgive me, I have made a typo. Let's go back and let's correct the typo. So we started off with x times the natural log of a. When I took the derivative of x times the natural log of a, I said the natural log of a is a constant, but what I wrote was the natural log of x. I meant the natural log of a here. That would mean we have a natural log of a here, and finally a natural log of a here. Be sure to correct that typo. So what we can say at this point is we now have a new rule. We have a rule that says that the derivative of a to the x is going to be a to the x times the natural log of a. Or we could write the chain rule version, which says that if we take the derivative of a to the u, that's going to be a to the u times u prime times the natural log of a. So there we have two new rules that we're adding to our list of derivative rules. All right. Next, now we're asked to take the derivative of y equals log base b of x. So what we know how to take the derivative of at this point is we know how to take the derivative of the natural log of x. We don't know how to take the derivative of log of any base b of x. Well, what this requires is this requires something that you learn in a pre-calculus class called the change of base formula. And what the change of base formula says is it says that if you have some log base b of x, you can rewrite this as log base c of x sorry, forgive me. You can write this as log base c of x divided by log base c of b. Now, let's go ahead and let's actually apply this change of base formula so that we can take the derivative of y equals log base b of x. So y equals log base b of x. We could rewrite this as y equals, well, I want to rewrite this in terms of a logarithm that I can differentiate. Well, the log that I know how to differentiate is log base e, also known as the natural logarithm. So let's rewrite this as the natural log of x divided by the natural log of that value b. Now what we can do is now we can take the derivative And in this instance, we don't even need to use implicit differentiation because we are taking the derivative of y with respect to x. And on the right side, we're taking the derivative of the natural log of x divided by the natural log of b. But the natural log of b is just a constant, so we could think about this as 1 over natural log of b times the natural log of x. We know that the derivative of the natural log of x is going to be 1 over x. And then dividing by this natural log of b just comes along into the denominator. So what we get here is, again, two new derivative rules. We have one rule that says that if we're taking the derivative of log base b of x, well, this is going to be 1 over x times the natural log of b. But if we apply the chain rule, we have a rule that says that the derivative of y with respect to x of log base b of u is going to be 1 over u times the natural log of b times u prime. You may also see this written as u prime divided by u times the natural log of b. So with this, I think I'm going to leave the notes here for today. We will pick back up with example 122 at our next in-class meeting. If you're looking for a completed set of notes, you can find the completed set of notes on Canvas. So thank you for watching, and have a good rest of your day, and I'll see you in class on Wednesday.